Hello, everyone, and welcome back to LearningHub. Have you ever wondered how machines can learn to generate incredibly realistic data or complex information efficiently? Today, we're diving into one of the most elegant and powerful concepts in modern deep learning, which is the variational autoencoder or the VAE. A variational autoencoder isn't just another neural network. It's a fascinating blend of deep learning and probabilistic modeling. It is the engine behind creative tasks like generating new images, music, or text, and it's also a key player in anomaly identification and representation learning. In this video, we're going to break down the complex mathematics and core ideas behind variational autoencoders, explaining exactly what they are, how they work, and why they are different from standard autoencoders. All in simple, easy to understand terms with clear visual examples. So get ready to unlock the secrets of generative models and let's get started. So first of all, we're going to recap autoencoders. We've already explained how autoencoders work in our previous video. If you haven't seen that video, I'll keep a link down below and you can go to that video and check it out and come back to understand variational autoencoders much better. So, and standard autoencoder has two main parts. The encoder, this takes an input image X and aggressively compresses it into a small low dimensional vector called the code or the latent space Z. And then this is the decoder. So this takes the compressed latent vector Z and tries to reconstruct the original input as faithfully as possible, resulting in the reconstructed output X prime or X bar. So the training process pushes the model to achieve two main things in autoencoder. First, the latent vector G should be as small as possible to force the encoder to capture only the most essential features of the input, that is the dimensionality reduction. And second, the reconstructed vector X prime or X bar should be as close to the input X as possible, ensuring the decoder can reverse the compression without significant loss of information. And then we train it by minimizing a reconstruction loss like mean squared error between X and X prime or original and reconstructed output. But there are problems with standard autoencoders. While great for compression, a standard autoencoder suffers from a major drawback, which severely limits its power as a generative model. The problem is that the latent space that we see here is not regularized. If you look at this code box or this latent vector box, we know that the values inside this particular code or latent vector are random and they have no meaning. The model only learns to map specific input data points to specific and isolated points in latent space. And second, it only learns the mapping between the input data X and its compressed vector Z. But it does not learn any semantic relationship or continuity between the latent vector themselves. Imagine the latent vector is a space full of islands. The autoencoder knows how to sail from a particular photo of a cat to its cat island and back. But if you try to sail in an empty water between the islands, the decoder produces meaningless and garbage output. These are huge gaps in space where the decoder has no idea what to generate. This lack of completeness in the latent space means we cannot sample a random point from it to reliably generate a new and meaningful piece of data. And this is the problem the variational autoencoder was designed to solve. So that's right. This brings us to the variational autoencoder, which solves the standard autoencoder's problem by making the latent space continuous and meaningful, which was not present in case of the standard autoencoders. So instead of having the encoder output a single fixed latent vector Z for every input X in a VAE, we learn a latent space which represents a multivariate distribution over the data. We'll look at the key goals here. The first is the semantic relationship, meaning we hope that this multivariate distribution captures the semantic relationship between data. For example, all food all food pictures should have similar representation, and like all animals, pictures should have similar representation in the latent space. Next is contiguity. Crucially, we want the latent space to be contiguous. This means if we take a point z1 representing a happy face and a point z2 representing a sad face, any point sampled along the straight line between z1 and z2 should decode into a face with an expression gradually transitioning from happy to sad. And why do we want this meaningful smooth organization in our latent space? Because it allows us to finally sample from this latent space to generate new data. Meaning, we can sample a random vector from the latent space, give it to the decoder, and generate brand new data that the model has not seen yet. Suppose if our latent space has areas representing bread, meat, and vegetables, and we sample a vector from space between those regions, the decoder should be able to generate a coherent image, let's say an image of a sandwich. So in essence, the VAEs ensure that the latent space is not just a bunch of random isolated points, but it is a smooth, continuous landscape where similar data points are clustered together, and moving from one cluster to another corresponds to a meaningful change in the generated data. To achieve this, the VAE introduces a key innovation in how the encoder works. So now let's look at the actual architecture change that we have. First, a quick note. The variational autoencoder architecture and its core concepts like the evidence lower bound or elbow, which we'll cover shortly, are not just academic. They are the foundations for cutting edge generative models. For instance, the variational autoencoder is the most important component of Stable Diffusion model, and they provide the crucial step of compressing and decompressing images into and out of the latent space. To understand the VAEs, we need three core mathematical ideas here. The first is the expectation of random variable. This is the average value of a function fx when x is drawn from a probability distribution px, and for continuous random variable it is calculated as an integral as shown here. The second is the chain rule of probability. This rule shows how to express the joint probability of two events like p probability of event x comma y using conditional probability, and the formula is given here. It means the probability of x and y both happening is the probability of y happening multiplied by the probability of x happening given that the event y has already happened. And finally, we need the Bayes theorem. So this is perhaps the most critical for variational autoencoders. It allows us to reverse the conditional probability. If we know the probability of x given y, Bayes theorem lets us find the probability of y given x and vice versa. So in VAE, we are interested in the probability of the latent space given our input data, meaning the probability of, let's say, latent space represented by z given the input data represented by x. The last essential tool in variational autoencoder is this Kullback-Leibler divergence or KL divergence. The formula is shown here. The KL divergence allows us to measure the distance between two probability distributions px and qx. In a VAE, we use this KL divergence to measure how close the latent distribution learned by our encoder, which is qz of x, is to a simple predefined, let's say a standard Gaussian form p of z. This is what enforces the regularization and makes the latent space smooth. It's important to remember some properties of KL divergence. First, it is not symmetric, meaning the divergence from P to Q is generally not the same as the divergence from Q to P. It's not a true gap matrix here. And second, it is always greater than or equal to 0. So the divergence will be 0 if and only if the two form P and Q are identical. This is the property we exploit in variational autoencoder. We push the learned distribution to be as close to our target as possible by minimizing the KL divergence in our loss function. Now we get to the heart of challenge in explaining our VAE model, which is fundamentally a generative model. So our ultimate goal is in building a generative model is to find the likelihood of our data, probability of X. We want to know how probable it is to observe the input X in our dataset. So we define the likelihood of our data by marginalizing over the latent variable Z. This uses the sum rule of probability or integral for continuous variable, where P of X comma Z is the joint probability of the data and the latent code. The problem is that this particular integral is intractable, meaning it's impossible or computationally too expensive to calculate exactly. Why? Because we need to evaluate this integral over all possible latent variables Z. The calculation is simply too expensive and complex here. Also, this intractability leads to a classic egg and chicken problem. To calculate the value of Px or the likelihood Px, we need the posterior distribution Pz of x, meaning the probability of code given the data, which we can find using the Bayes theorem. But notice that Px itself is in the denominator. So to calculate Pz of x, we need Px, which is the very thing we found to be intractable. We can't find one without the other. Since we can't find the exact Pz of x, the solution is to approximate it. This is where the variational part of VAE comes in. We introduced a second distribution Qz of x, which is defined by our encoder network. This network is parameterized by phi, and its job is to give us an approximation of the true intractable posterior p theta of z given x. So we want to find this particular term here. Sorry, it should have been q phi z of x in this particular part. Now we perform a clever bit of math to rewrite the logarithm of our likelihood log p theta of x. This involves a sequence of transformations to isolate the term we can actually compute. The final derivation using the definition of expectation and KL divergence results in the following fundamental equation that we see at the end here. And this is a profound result. It decomposes the log likelihood of our data into two key components. The first is the evidence lower bound, this particular term here, and the second is the KL divergence, this particular term here. Since the log p theta of x is a fixed value for our data and the KL divergence term must always be greater than or equal to 0, minimizing the total loss means maximizing this elbow or evidence lower bound term here. Because we cannot calculate the true log likelihood, we use elbow as a proxy. Maximizing the evidence lower bound is equivalent to maximizing the likelihood of data, while simultaneously forcing our approximation q phi z of x to be as close to the true posterior p theta z of x. This elbow term, which we use as our objective function, is the secret sauce of VAE. Let's break down what the elbow actually means in terms of a loss function in the next step. We just extracted the foundational equation of the VAE, which states that the log likelihood of our data is equal to the evidence lower bound plus the KL divergence term. Since the KL divergence term is always greater than or equal to 0, we can infer a crucial inequality, which is our likelihood of our data is greater than or equal to the elbow. This confirms that elbow is a lower bound on log likelihood of our data. The key to training the variational autoencoder is to maximize this elbow term here. When we rearrange the elbow into its most useful form, we see that it naturally splits into two terms, giving us the VAE's two-part objective. Maximizing the elbow means we are simultaneously doing two things here. The first is maximizing the first term or the reconstruction loss. The first term, EQ of phi z given x, and then this particular term here is the expected log likelihood of the data x given the latent code z. Goal, we want to maximize this particular term. What it means in practice? This is the reconstruction likelihood of the decoder. It means we are training the decoder to be really good at taking a sampled latent code z and accurately reconstructing the original output x. This is exactly like the reconstruction loss in a standard autoencoder. And next, we want to minimize the second term or the regularization loss. The second term is the negative of the KL divergence between our learned distribution q phi z of x, which is the encoder's output, and a prior distribution p theta of z, which is our assumed structure for the latent space. The goal is to maximize the elbow, and to do it we need to minimize this particular negative term here. What it means in practice? This is the regularization loss. It forces the distribution learned by the encoder to be close to our simple prior distribution, which we usually choose to be a standard Gaussian normal form centered at 0. So now let's move to the VAE training part. We'll look at this particular diagram here, which properly summarizes the concept. The encoder q phi z of x learns to map the input data x into a probability distribution with mean mu and variance sigma square in the z space. The KL divergence term then forces these learned distributions to be as close to the prior. This ensures the latent space is smooth and continuous. And then the decoder p theta z of x learns to reconstruct an image x from a sample z from the encoded form here. And this is the core idea. The VAE or the variational autoencoder is a beautiful trade-off. It must achieve good reconstruction like a standard autoencoder, and it must also maintain a well-behaved regularized latent space. So how to maximize this elbow or the evidence lower bound? So when we have a function to maximize, we usually use gradient ascent. We take the gradient with respect to the model's weights and adjust them to move along the direction of the steepest increase. However, maximizing the elbow presents a serious technical challenge. We cannot directly backpropagate through the sampling step. Look at the elbow equation again here. The expectation is taken over z sampled from the encoder's output, which is q phi z of x. We need to differentiate this entire expression with respect to the encoder's parameter phi. And the standard way to estimate this gradient is called the score estimator. But as noted here, it has very high variance and is impractical for our uses. And it also leads to unstable training. This means we need some form of a trick to maximize the elbow efficiently and enable backpropagation. Now this trick is called the reparameterization trick, and we'll cover it next. So we just established that while maximizing the elbow is our goal, the random sampling step inside the expectation makes it impossible to directly use standard backpropagation. We need a way to pass the gradient signal from the loss function back to the encoder's parameter phi. This is where this reparameterization trick comes in to play. This is the crucial innovation that made VAEs trainable. VAE is trainable. It's a clever way to separate the randomness from the parameters. In the VAE or the variational autoencoder, the encoder outputs the parameter, the mean mu and variance sigma square of q phi z given x. The latent vector z is then sampled from this particular form. Since sampling is a non-differentiable operation, backpropagation stops there, right before mu and sigma square. And its solution: instead of sampling z directly from q phi z of x, we reparameterize the random variable z. We introduce a standard fixed and independent random variable epsilon, sampled from a simple known form like a standard Gaussian form. We then calculate z as a deterministic function of mu, sigma, and epsilon. The encoder still outputs mu and sigma, and the randomness is externalized to epsilon, which is outside the network's parameter phi. Now the creation of z is a deterministic operation, addition and multiplication, making the entire path from the loss function back through the encoder's parameter differentiable. This technique gives us a new estimator for the gradient, often called the stochastic gradient variational bias, meaning SGVB estimator, which has less variance than the previous impractical approaches. So let's quickly bring it all together by looking at this entire process here. Input is an image x that enters the VAE. Encoder q phi is z given x. The encoder processes x and outputs two vectors for a latent space, which is a mean vector and a variance vector, often log variance for stability. Reparameterization trick: we generate z equals to mu plus sigma into epsilon. This is the sampled latent vector. And the decoder then takes this reparameterized z and then reconstruct the image x bar. Loss or elbow: the network is trained by minimizing the negative elbow, which combines the reconstruction loss, measuring how close the reconstructed image is to original image, and the regularization loss or KL divergence, measuring how close the learned form are to a standard Gaussian prior. This architecture ensures the latent space is smooth, continuous, and meaningful, allowing us to generate reliable new data by sampling from a prior form and passing it to the decoder. And that's the power of variational autoencoder. We have discussed the two parts of VAE loss and the reparameterization trick. Now we'll look at the final concrete formula for VAE's loss function, which neatly summarizes everything we've covered. Remember, we want to maximize the elbow term. In ML, we typically define a loss function that we want to minimize. So we take the negative of elbow. So the VAE loss, this particular term here, for a single data point xi is approximately defined by this particular function here. Here we are minimizing this function, meaning we are maximizing the elbow. Let's break down the terms in final loss function. Term 1 is this particular term here, is the regularization loss or the KL divergence loss. So the first part or the large sum is the KL divergence term, which we got from or which we got in the evidence lower bound formula. It is calculated using the mean mu and the variance sigma square, outputted by the encoder for each dimension j of latent space. Here the prior assumption p theta of z is the simplest possible, a centered isotropic multivariate Gaussian. This means the mean is 0 and the covariance matrix is the identity matrix. And the goal is to minimize this particular term. And by minimizing this term, we force the distribution of the latent codes learned by the encoder q phi z of x to resemble this simple standard Gaussian. and this is what recreates or creates the smooth and continuous latent space needed for generation. And the second part of the negative, sorry, the second part is the negative of the reconstruction likelihood term. The goal is to minimize this term, and to minimize this term, we must maximize the likelihood of the reconstructed data. This term measures the difference between the input image X and the reconstructed image X bar or X prime. So if you are modeling real valued data like p theta x given z, it is a Gaussian form, and minimizing this term is equivalent to minimizing the mean squared error. And if you're modeling binary data or pixel values, then the same is in a Bernoulli form, and minimizing this term is equal to minimizing the binary cross entropy loss. So in summary, the variational autoencoder is a single model trained to balance two opposing forces. The first is reconstruction, meaning accurately reconstructing the input image, and the second is regularization, meaning ensuring the latent space is well organized and smooth for generation. So by successfully balancing these two, and by using the reparameterization trick to enable training, VAEs successfully bridge the gap between deep learning and probabilistic modeling, giving us a powerful tool for unsupervised representation, learning, and most importantly, reliable and meaningful data generation. So, thank you for joining us on LearningHub. We hope this deep dive into variational autoencoders has been helpful. If you have any questions or want to cover any other complex topics, please let us know in the comment below, and don't forget to like and subscribe. See you in the next video.